All right. So, ladies and gentlemen, let me tell something about the lattice dynamics and trimeron order of the Verwey transition and magnetite. So this work was done in a large collaboration with some other groups, including experimentalists from MIT and others. But mainly the theoretical part and calculation were done by myself and Przemysław Piekarz from Polish Academy of Sciences in Krakow, Poland. All right, so here is the list of the authors of the basically several works which we devoted to this Verwey transition and all this material. And before I will start, I would just like to introduce about our group and where actually the Technical University of Ostrava is located, and the Czech National Supercomputer as well. So it is on the east part of the Czech Republic, or basically on the border with the Poland and Slovakia, in the third largest city in Czech. And basically here is a list of clusters which we went through. The 2012, the year when basically this supercomputer, national supercomputer of the Czech Republic was founded. So the first computer was basically outside. It didn't have even a building, so it was in container, having about 3,000 cores. Then in 2014 we erected this nice building with the data cell, which we equipped in 2015 with the cluster Salomon, which was at that time about 40, the fastest supercomputer in the world later on. And basically this month he's actually ending the production of the calculations and will be disentangled. So the one in the container actually was replaced by Barbara 1 year ago. We also have a special machine just containing the 16 GPU cards from NVIDIA. And the newest one is actually a Carolina. This is a supercomputer which is also in the top 100, but it has two parts. So basically the non-accelerated is something about 78th place, and the accelerated one is about 100 something. So altogether actually will be in the first 50. So it has over 96,000 cores. So you see that's a dramatically increase from the basically 9 years ago. All right, so let me introduce the group actually and what we are working on. So I'm especially interested in the phonon interactions, and with that respect, simulation of the heat transfer, like for the nuclear fuels, as well as, of course, for magnetic materials like the magnetite I will talk about. For the multiscale magnetic materials modeling, there is an expert, Pablo Nieves, who actually is developing a magnetostriction program and crossing the scales, including atomic spin dynamics and finite element methods. For the we are interested in alloys, we have a project actually for the fusion reactor first of all application, and these are based on the alloys of tungsten and on basically the phase stability and description of the miscibility gap and how to actually change it or put it to the lower temperature and increase the miscibility. This is the expertise of Andrzej Kozalava. For the large simulations, taking actually over 100,000 atoms with DFT. We have an expert of actually Sergio Arapan using a conquest code, actually scaling DFT code as well. Is this slide is there's presented that he's expert in molecular dynamics. So for very large systems and with so-called React force field, which you have. And then for the disorder, either chemically or magnetic, we have a junior basically scientist expert from Charles University, and this is Jakub Sebesta, which we have analyzed the magnetism in the high entropy alloys in the recent years. All right, so now back to this Verwey transition. So you know already by Karl Renger in the beginning of the last century, there was this stability measurements actually and found a peak. Actually this appeared in his thesis, and it was supervised by Albert Einstein, and of course he didn't have the time to do it, but he found out this anomaly around this 125K, And later on by Verwey, it was actually measured that there is a drop in the conductivity, very large drop, several orders of magnitude, and this temperature. And he already speculated that this actually could be that there will be a phase transition from this cubic structure of the magnetite. And in the cubic structure, you know, we have two positions of iron, the tetrahedral and the octahedral. And the octahedral position is actually a combination of this iron 2 plus and iron 3 plus, so it is overall like 2.5 nominally. And this actually will produce certain ordering, of this different charge on these iron sides. And what we have discovered, so we identify finally the structure, especially also showing the lattice dynamics. So it means stability of the structure, which is actually so-called CC structure, which is below the 125 K. So already Verwey actually speculated that there will be a charge ordering of these iron atoms with different charge. And later it was actually called a trimeron, so a quasi-particle, which has an iron 2 plus in the centrum and iron 3 plus at the ends. And these trimerons have a certain order actually in the structure. So it could be actually connected to this iron 2 plus, one of them, but not all of them actually. So this is this charge ordering which could be behind it. And it is basically, you describe which kind of, let's say, states are responsible, how they differ for this A and B side. So you see then in the iron 3 plus A side, actually this T2G, Eg are very low in the one channel, and the other one are unoccupied. Whenever this 2B side have not only that the opposite because of the different crystal field, but this T2G on the one of the channel is actually very close to that Fermi level. And this, in the higher valency, actually, you see that this is, they have basically, they do not have this T2G occupied close to the Fermi level. They are basically empty here. So these are the differences in this electronic structure schematically. And so this was known for the cubic structure actually and everything, but and of course there were many experimental studies about the Verwey transition, and what they found already that there is a softening of the C44 elastic constant. So the C44 is a elastic constant responsible responsible for the loading along the body diagonal. So it's called trigonal deformation. So actually this is the resistance for this deformation mode. And it shows actually a sudden drop to this 125K. So basically at this Verwey transition, and it's basically was somehow like explained in the coupling with the elastic strain to some fluctuation of certain lattice dynamic modes, because this long wave limit actually, this is basically related to the acoustic wave of the phonon, certain symmetry. So that leads us also to calculate the lattice dynamics and maybe to find out actually which kind of the structure could be below the Verwey transition. So we use this density function theory, and for the calculating the phonons, the Parlinsky-Kavazoya method. So calculating Hellman-Feynman forces, basically we display the atoms and we calculate the forces not only on this display one, but also what it induces on the other atoms in the large supercells. And then we calculate for constant matrix and diagonalize it. And with this dynamic matrix, we obtain basically the frequency of the phonon modes. And if they are real, then the structure will actually exist. If they are imaginary, then we have to distort the structure along some way. So it can actually tell us in which low symmetry structure we should actually continue searching for that. All right, and that basically comes with that we calculated the cubic structure. What you can see basically, it's without correlation, let's say Hubbard model. I will not talk about this detail, but this is just some localization of the electrons close to the atom of the certain shell. And what happens actually then when we increase this to 4, that first of all we got better agreement of this acoustic or these branches basically, but also there is a, if we basically use this equal 4 and then we distort from these cubic structures to so-called P2C. So this is not the ending structure, but it's the first model actually. And then we opened the gap, and that was at X point, and there was something which was observed here and was not visible basically. So that was the first indication we are on the good track. So we ended with P2C structure, but from that we derive the correct one, which is actually 2 times more complicated CC structure. Of course, there are some structural fluctuation about the magnetism, but this I will not talk about, which actually again shows a drop anomaly at the Verwey transition. So we compare, of course, our vibrations at the gamma point with measurements, like it could be compared either to infrared frequencies detected, or it could actually can be detected by the Raman, depending on the symmetry. So you see this is the P2C structure versus just the simple few modes of the structure. So I think that this actually is pretty good. And of course, there was a detection that there are certain forbidden modes which actually are not allowed in the cubic, but they are also observed. So there is some certain actually fluctuation between this charge ordering and the phonons, even above the Verwey structure, somehow persists. And the question was actually how it is. And then, of course, later in the temperature, one has only this T2G actually, which are allowed. And this was also confirmed by the MIT group actually with the optical conductivity measurements and pump probe experiments. But now was actually the question, what can be this Verwey transition from this cubic to P2C to CC structure, actually, what it could be behind, actually. Is it a rotation of this trimeron? But if we did it, the calculation, it was just of the 1 EV, so that was so much, actually. The instability was about much more less. So there was something like a tunneling current, so-called polaron tunneling, which was of the order of only 5 millieV. And then we found out that there is basically certain fluctuations. So once we put the atom close on this trimeron and then the others, that we calculated that this is actually the one which could be, which this atomic displacement could be behind it, actually. So it is something like a charge fluctuations and the phonons, which are all together. And at the end, when we have the phonon calculation for the CC structure, and we compare it with the actually inelastic neutron scattering. So this is what it is, and it has actually a very nice, I would say, agreement between the theory and experiment. And actually, I don't have a figure here, but you cannot have a phonons in this cubic structure that is so high actually in the room temperature that there is no such a good agreement. One can see in the VSB 2021 for it. And we give some explanations. And of course, if you look at the dispersion, so you see that there is basically inelastic neutron scattering, and once we go below the Verwey transition, which is actually the green, that we have the best actually agreement with the optical as well as the acoustic branches. So that was also nice. So more one can see in this publication in this Nature Physics, and the discovery of the soft electronic modes of the trimeron order. And then I come to the conclusion of the whole talk that basically this DFT reveals this strong electron phonon coupling, which opens the gap, and including this monoclinic distortion, this P2C, and then it leads to CC structure, which is actually the lowest ground state of the magnetite below the Verwey transition. The inelastic X-ray scattering is supported a little bit that anomalous phonon broadening above TV. So indicates that there is a strong anharmonicity above the TV, and that's why the classical quasi-harmonic phonons cannot explain the phonons of the cubic structure. So there is a certain phonons with the critical fluctuation which actually can persist over the TV, but that more about this trimeron phonon coupling magnetite could be found in the recent feasibility when we calculated with TMAG again. More details about the mean square displacement, which actually explains the behavior of it. And we also offer several basically positions in our group to study this magnetism as well as phonon-phonon interaction. Thank you for your attention.